Imagine a star denser than anything you can possibly comprehend, spinning on its axis hundreds of times every single second. Picture a celestial object so compact, a single teaspoon of its material would outweigh Mount Everest. This spinning stellar remnant shoots out powerful beams of energy from its magnetic poles. As this cosmic lighthouse sweeps its beam across the vastness of space, if Earth is in its path, our radio telescopes pick up a pulse. A steady, rhythmic beat ticking with a precision that rivals our best atomic clocks. It's a message from the ghost of a long-dead star. So what is a pulsar? It's a type of neutron star, the collapsed core of a massive star. A massive star runs out of fuel it can no longer support its weight. The core collapses under gravity, a supernova explosion follows. The story of a pulsar begins with the death of a giant. It all starts with a star far more massive than our own sun, a true behemoth living a fast and furious life. These giants burn through their nuclear fuel at a prodigious rate, fusing lighter elements into heavier ones in their scorching hot cores. For millions of years, the outward pressure from fusion balances the inward crush of gravity. But this cosmic balancing act cannot last forever. Eventually, the star runs out of fuel. The furnace sputters out and gravity finally wins. The star's core collapses in less than a second. That implosion triggers a rebound shockwave tearing the outer layers apart, a supernova. For a brief period, the explosion can outshine its entire host galaxy. The blast scatters heavy elements across space, the stuff of planets and people. Left behind in the expanding cloud is the crushed remnant of the core. This remnant is a neutron star. Its gravity overcomes the forces that keep atoms apart. Electrons and protons are squeezed together to form a sphere of neutrons. A neutron star is only about 12 to 15 miles, around 20 kilometers, roughly the size of Manhattan Island. Yet it packs up to 1.5 times the sun's mass into that volume. The density is staggering. A sugar cube of neutron star material would weigh about 100 million tons on Earth, equivalent to the weight of the entire human population. The collapse also concentrates the star's magnetic field, amplifying it to trillions of times Earth's. The intense magnetic field and rapid spin work together to accelerate particles near the magnetic poles, creating powerful beams of radiation that define a pulsar. These beams, radio waves and other forms of light, shoot out into space. Born from violent chaos, the pulsar is an object of incredible order and precision. A celestial clock ticking cosmic seconds with unwavering regularity. The discovery of pulsars is a fantastic story of scientific serendipity, sharp observation. It happened in 1967 at Cambridge University, where a young graduate student named Jocelyn Bell was meticulously analyzing data from a new radio telescope she had helped build. Her task was to hunt for quasars, which are distant, bright galactic cores. As she sorted through miles of chart paper recordings, she noticed something odd. A tiny, faint signal pulsing with an almost unbelievable regularity. It appeared as a bit of scruff on the data charts, not a quasar, not simple radio interference from Earth. The signal pulsed every 1.33 seconds. At first, the research team, led by Anthony Hewish, considered every possible explanation. When those were ruled out, they half-jokingly nicknamed the source LGM-1 for Little Green Men. The discovery of multiple sources made the alien hypothesis highly unlikely. Pulsars are far more than just cosmic curiosities. They are invaluable tools for scientists. Because their pulses are so incredibly regular, they function as nature's most precise clocks. The most stable of these are the millisecond pulsars, older neutron stars spun up by stealing matter from a companion star. Some spin over 700 times per second, and their timing is so predictable it can detect the faintest ripples in space-time. Those ripples are gravitational waves. Pulsars have been used to test general relativity. That energy loss should make their orbit shrink. A pulsar's radio beam passes through the interstellar medium on its way to Earth. gas dust charged particles. This material slightly delays radio waves. Lower frequency waves are slowed more than higher frequency ones. Measuring that tiny delay gives the total free electrons along the sightline, letting astronomers map density in our galaxy. They could one day become practical beacons for interstellar navigation. What other secrets are they ticking out for us to find?